Autonomous garden, and so here we have a prototype of what we were doing. So we prototyped it with using a Arduino. So here we have a system that we have an external battery powering up all of our electronics. So the motors, sensors, and the Arduino itself. So from here, we set a timer so this pump turns on at 7.
Comes in through a solar panel and enters our first buck converter where it regulates to 12 volts to make sure there's no transient spikes. It then feeds into our battery at a constant rate. The battery then puts out another 12 volts to another buck converter, converts to 5 volts where all of the sensors and microcontrollers will be running. This is the MOSFET PCB that will receive the signal from the microcontroller. It'll convert back to 12 volts, let it through for our 3 pumps and our solenoid. And then the 5 volts will be for the LCD that gives us the temperature, the light, and all of the pump timers and the pH. This was the quick and dirty prototype. After this, we wanted to go with a little more embedded level. So Adrian took over from there and created another GUI.
Okay, so this one uses a Raspberry Pi. So we have a user interface. So right here, we can display the data. So sensor data is right here, time. We have water sensor, we also have light level, and then we have the pH and the temperature. So also here, see it? So we also have lights indicating which pumps are turning on. So see how we have the pH. The pH is supposed to be for the plant around 5.5 to 6 pH. Right now it's at 6, so it pumps in some of the solution to dilute it so it can go to the values that I say right now. So right here for the water line sensor, we also have pump controlling, getting controlled by the input of this. So it would be sticking out like this. So water comes in and then the buoyancy of this makes it float up. So this pump will turn off. So that's how we have that. So on our user interface, we also have a couple of options. So we have manual. We can send email using a press of a button. And then we also have the camera. So it takes a picture. So can you show that? Right here, when you send the email, it shows a picture that it takes from the camera, and then it also shows some of the data from the interface. So right here, we can also manually turn on the pumps. So let's say pump 5 is not on right now, so we'll go to pump 5, which is the basin pump. So if I turn it on, it should turn on. You get it?
This is a digital signal processor. We take in an audio signal at a sampling frequency of our choice. So right now we're reading in our line in from a sample board at 48 kilohertz. And then we just do whatever we want to those samples. We interpret the information, modify them, multiply them by, like, for example, a sine wave multiplier or an overdrive multiplier. And then we just feed it back out to line out, and then you can hear the effects.
Yeah, so right now we're working on the sine wave. So what we're going to do is just going to play some notes. So that's just a little example of what we can do with our effect.
Autonomous greenhouse. We can see here our photoresistor. So when there's light, the lights are off. When there's no light, they turn on automatically. It's autonomous. Here behind it, I have a water tank with the water pump. And right here we can see the display.
Yeah, you can monitor.
Now here we have a humidity sensor on this side. Moisture sensor down here. You can see it right here. So when there's no moisture, water pump turns on. You see the water running, right? Record that, buddy. All right. So now we have enough water.
And also for the temperature, there is a fan. It's not working right now.
Yeah, you can see
Make it hotter.
Yeah, the smaller.
125 degrees centigrade.
Now the fan is on. You see it working, right?
Yeah.
And then here we have the rest of the circuit in the black box.
Yeah, for our photoresistor, we use an ADC chip to convert from analog to digital. So we can see all the data here. Okay, so basically we're using a Raspberry Pi to drive the motors, and we're using a time-based time to volume algorithm to figure out how much we're dispensing. And here we go. This is a rum, vodka, and mix, so it might come out a bunch of funny colors. Usually brown. Hot because our temperature is at 82 degrees right now, but it'll speed up in a little bit. If you open the top, you can see where everything is. You simply put your alcohol inside and then cap it, and it'll just run through the motors. And the GUI will prompt itself as when you start it. That's basically it.
Senior product is a voice controlled water car. So the way this works is we're using Google's API as voice recognition, and we send commands to Raspberry Pi, which will determine motor functions for the water car. So as you can see here in the diagram, we have Google's voice API, which sends commands to Raspberry Pi, which we have controlling. We use an Arduino at first for our sensor feedback, but we're not using an Arduino anymore. We have it running straight to the Pi, and that's going to determine the motor feedback for the actual sensors and for the motor feedback of the actual the definition for our code and how it works.
Okay, so when you say "Okay, Google," the light lights up and it knows that it's ready, and then it'll be ready for command. Okay, Google. Zulu. Google. Yankee. Okay, Google. X-ray. Okay, Google. Alpha. Okay, Google. Eagle. Okay, Google. Delta. Okay, Google. Eagle.
So our project is Find Me Indoor Localization Solutions. So I'm Kevin, this is Sam, this is Austin, and we're using ultra wideband to track something indoors. So this is our software. So what we have here is a system of anchors and tags, the tags being the device that's being tracked. So the tag is right here. So this is being tracked around the room, overlaid on the floor plan with an accuracy of about 6 inches and a refresh time of about a second. Range of this is about 300 meters, and we operate with a bandwidth of 3 to 10.6 gigahertz. So this is good for things like asset tracking, tracking employees, robotics, virtual reality, and it's able to operate in extreme conditions. Let's take a look at the board. So this is the board of the tag that is being tracked. You have here your DWM1000 chip with the integrated antenna, and that's connected into our circuit and our microcontroller.
We have two drones. One does search, one does rescue. Our search drone has a Raspberry Pi and a Raspberry Pi cam on it, and it is hooked up to a Pixhawk 4 flight controller. Our search drone goes to a GPS location and starts recording video and confirms if there's a victim there or not. When the drone comes back and we review the video, our rescue drone, once the victim is confirmed to be at a GPS location, then our rescue drone will go to that GPS location and drop a payload. And our rescue drone is using a Navio 2 with a which is a hat for the Raspberry Pi, and it is our flight controller. Our dropping mechanism is just a servo. And we basically have GPS, like our whole mission to make it autonomous is to go to a GPS location and then at that location set a servo PWM signal to open up the servo and drop our payload. And then return home and land. And yeah, that's basically it.
So what we have here is our haptic robotic arm, and so the concept of this is that whenever you move your actual arm, the robot arm will mimic it. So we have an exoskeleton attached to your arm, and that should mimic it. And so we have a demonstration here. The exoskeleton attached to Calvin, the robot arm, and it should mimic it. Now remember, this is all done wirelessly. So this is done through serial XB data. So for the most part, whenever the accelerometer data comes in, it'll come back and appropriately be assigned to each servo.
So this is our in-car voice control system. Right here we have the AIY voice kit. This is the AIY voice kit, and it uses the Google Assistant API, which we use to create commands that the Google Assistant can understand in order to send messages to the other Raspberry Pi, which has the Pi Can 2.
So the second Raspberry Pi is the receiver Pi, so it's always getting data or the voice command from the Google Assistant. So from there, we have a program to send CAN messages into the car, and these separate CAN messages allow the car to do separate commands. So for example, headlights, to turn on the wind, power on the lights in the car, open, close windows, so on and so forth. So we do this via a DB9 cable, which is connected to the PiCan 2 into the OBD2 port of the car. And in order for us to get these CAN messages, we use the PCAN to USB, which also has the OBD2 connector. And based on these messages, you can do limitless things for the car. So this is the video.
So basically the way it works is the two green lights indicate that the parking lot is open, or the parallel parking space is open. So say out of my car, I come in, we have the two blue lights. And if I'm too far forward, the red light will tell me that I'm too far forward. If I'm too far back, it will tell me I'm not in the car anymore. That is telling me I'm too far back. If I'm dead center, the two blue lights will turn on, and there's a 5-second time. If you want to come over here, you can see on our GUI the countdown. So that's our GUI. Basically, the person would get out at this time, and they press time to begin. They choose the amount of time that they want to stay, and then press pay. And then down here, we have a RFD reader, so they have something like this or a card or something. Basically, they tap here, and once they're paid, it'll go to their screen telling them how much time they have left on their meter.
Our project is called Farmer. It's RF energy harvesting. So basically what we have set up here is an RF generator set for 70 megahertz. And this is our simulated transmitter. So this transmitter can be a radar, such as like an altimeter, any sort of transmitting device. We're transmitting 1 watt of power from the generator. This is our receive antenna. So we're transmitting the 1 watt. Our receive antenna is going to pick up the RF energy, and it's going to be sent through a rectification stage. Once that RF energy is rectified, it's now DC voltage. So that DC voltage is going to be put into our RF harvesting stage, which is called the BQ255 harvester. That voltage is going to be boosted from 200 millivolts to 3.3 volts. Once that 3.3 volts is boosted up, we're able to charge a battery. So once that battery is charged, we're able to boost up that 3.3 volts to 5 volts. And we're able to charge, this is just an example of a type of device that we can charge. So we have 5 volts outputted. We're about 70 milliwatts, so we're about 0.35 watts. So we're transmitting 1 watt, and we're able to get 0.35 watts, which is only efficiency of 35%. But if you think about it, we have the existing RF signals already there, so we're kind of just repurposing the RF signal. And this can be any type of sensor. It doesn't necessarily have to be a wearable device. It could be any low power sensor. And that's our project.
For our senior project, we decided to create a tongue-controlled electric wheelchair. So basically, we have a couple of mouth guards fashioned with force-sensitive resistors. This one controlling it forward, right, left, and then reverse. So basically, as the user applies pressure with their tongue, they apply it onto the sensor, and then depending on how light or how hard they press it, the chair will move in that direction at speed corresponding with the amount of pressure they put on it. So the FSRs are connected via wires to a Raspberry Pi in the back, and then the Raspberry Pi is connected to DMC controllers, motor drivers on the bottom for each individual motor, controlling the motors. So. The main problem we had is that there's a lot of saliva buildup when the user puts it in their mouth, obviously. So to combat that, we had to wrap it in plastic wrap. This would allow the sensors to not get messed up or give us invalid inputs from the sensors. And also it wouldn't apply that much pressure to the sensor, so we wouldn't get that much reading on it. It really worked out.
We are Ponderosa 2.0. We're the fluids aspect of it. So we basically handled all the fluid dynamics of the Ponderosa project. What that encompasses is using Ponderosa's existing pumps to get the fluids from their drums, as you can see in this photo, to our end effector to the actual gantry design. So how we did this is we want to make it as sustainable and as efficient and as cost-friendly as possible. So at the end of the day, VR is able to use this design. The manufacturing plant started in World War II, so we want to last just as long as that, and we want to be cost-effective and efficient.
So our big part of this project is designing a nozzle body that's automatically controlled. Since traditional paint guns are manually controlled by a trigger, we're using a solenoid in order to release what is the needle there. So once that opens, paint can come out of the gun. Once it closes, it stops coming out of the gun. So what is this? Here's a picture of the spray pattern that it can do. We have 9 different nozzle bodies mounted onto the end effector here, which the end effector is mounted to the end effector motor. So the control systems will control this motor in order to rotate as the wreaths come down the line in order for us to correctly cover the wreath decoration in enough lacquer for it to be shiny. Here's a small model of it, just a little easier to see. So wreaths will come by the end effector, and as they're coming by, this line is moving at a steady rate. This end effector will paint these or cover these wreaths with lacquer.
So the purpose of the project is to basically design the end effector itself and design how we're going to physically automate the fluids getting from one drum to the wreaths themselves.
And so another scope of the project was to implement the entire system into an already existing plumbing system at BR. And so this is a replica of what the actual paint room looks like. So you have your drums of lacquer here, and so we just had to integrate their already existing plumbing system into our robot, which is this robot is replacing the man that is spraying the wreaths currently. And so in order to make it a safer and less hazardous environment for the workers, we're replacing him with the robot. So, yeah, that is the fluids.
Whenever you're ready. So our part of the project was to do the mechanical assembly of Ponderosas. We use aluminum alloy, which are like kind of human Legos in a sense. So they have these grooves within the rails that allowed us to seamlessly integrate any fasteners or nuts and bolts into our design. So our design has 2 triangle frames and then a gantry system in the middle that supports the end effector, which Angel talked about previously. Our main objective was to create a sustainable frame that could be used for years to come and that could withstand the moments of the end effector. That's about it for our mechanical side. It consists of pulleys, gantry system, and the framework to support it.
Okay, so our project was Project Ponderosa, and so what we did was we worked with the Boys Republic and Chino Hills to help automate part of their painting process and their manufacture of their Christmas wreath. So what our machine does is it applies the lacquer onto the wreath, and how it does that is it first detects the wreath coming down the line, and then the gantry design of the robot moves in either the X direction or the Y direction depending on the size of the wreath. If it's a 22-inch wreath, then it will just move in the X direction. If it's a 28-inch wreath, then it will move in the Y direction and then in the X direction. Okay, so the end effector is not 9 solenoids. So if it is a larger wreath, then all 9 solenoids will turn on, and it will cause the mechanical pump to actuate and apply the lacquer. So if it's a 28-inch wreath, then it uses 9 solenoids. If it's a 22-inch wreath, it will use 6 solenoids. And we also have air valves also involved in the end effector. Some other inputs that we have is the limit switch. So the limit switch resets the stepper motor every single time on the x-axis and on the y-axis, so that the microcontroller always knows where it is. It's a project.
The computer vision part. So basically what we're doing is trying to track the velocity of wreaths so that we can tell when a wreath is entering the work area for the controls team. And also we're doing a QA sort of thing to tell when a wreath is properly lacquered and when a wreath is improperly lacquered or if it got missed somehow or something. So we're intending our work area to look something like this. We're going to have like a magenta background that the wreaths are going to track across. Or they're going to go this way. And we're using some OpenCV functions to separate the colors, basically. So we have everything that's in the magenta background gets turned to black, and everything that looks like it's probably a wreath gets turned to a white shape. And it's able to find like the leading edge of a wreath by checking for a column that's all black, followed by one that is it has some amount of white in it, and then it stores that that value that it got for the next iteration. And once it has like multiple position measurements, it can calculate instantaneous velocity, and then it averages it over the last couple seconds or whatever. and it's able to use that velocity measurement to estimate when a wreath has entered the work area, and then it sends a flag when the timer's counting all the way down. So over here on my laptop, I have a demonstration on what the thing looks like when it's working. So up top is the normal vision, and down bottom is the transformed image. So if we move a green object in front of the camera, it's able to track it, and it's doing its thing. It's really hard to read because it's going so fast. On this computer, we have a slowed down version of it, running by frame. It's a little easier to read, and that's the main part of it. And then for the QA section, we're going to be trying to estimate if a wreath is lacquered or not based off of saturation of like a wreath. We're going to have like a really strong light shining on it, and if the saturation is too low, then we're going to say that it's probably improperly lacquered and throw a flag, and then the controls team can try to error correct to some extent with that.